class, this is lesson 7C. In this lesson we're going to just look briefly at the Krebs cycle. This won't take a large chunk of our time, but we do want to make sure we understand the Krebs cycle. So where we left off. So we left off in our story at the end of glycolysis and the transition reaction. We had taken a 6-carbon molecule and we broke it down into two 3-carbon molecules called pyruvate. And then we removed a carbon during the transition reaction and we got this 2-carbon molecule called acetyl-CoA. So that's where we start. That acetyl-CoA is going to be part of our next part of this Krebs cycle, and so we need to understand what happens to acetyl-CoA. So the Krebs cycle is a cyclical pathway. It'll look a lot like the Kelvin cycle to you. And it takes place in the mitochondrial matrix. It takes place in that fluid inside the mitochondria. If you're not quite sure what mitochondrial matrix is, you may want to look back at a couple lessons when I talk about energy organelles. Rewatch the energy organelles just to get an understanding what that mitochondria looks like. It's got that folded inner membrane with the cristae and then the fluid called the matrix. So the Krebs cycle takes place in the mitochondria, but it takes place in the fluid. This could take place in the fluid. The big thing that happens in the Krebs cycle is we're going to take acetyl-CoA and we're going to convert that to a whole bunch of these high energy electron carrier molecules. So we're going to convert them to these electron carrier molecules called NADH and FADH. I like to attribute NADH and FADH to a check. Checks are only good if you bring them to the bank and cash them. They're not good right away. You can't take a check to the store and spend it right away. You have to first cash it in for cash before you can use it. So NADH are worth energy, but they have to be cashed in at the electron transport chain first. So that's the purpose of this Krebs cycle, or citric acid cycle, also called, is to make a whole bunch of these NADH and FADH, or write us a whole bunch of checks out for ATP that we can cash later. So we also create a little ATP, but not much. That's not really the big part of this. The big thing that the Krebs cycle is going to do is to generate tons of these high energy electron carrier molecules. Okay, let's take a look at it. That's about all you're going to write down for this. There's no more writing. We're just going to get a good understanding of the process that's happening here. So let's talk about it. Here is the citric acid cycle. Now, do I care if you know the names of each of these individual molecules, like citrate, isocitrate? So do I care that you know those? No, I don't. But I want you to know the general idea. So here's where we start. We ended with that acetyl-CoA, or acetyl coenzyme A, so we're starting here. And as you can see here, acetyl-CoA goes into this process. It meets up with this molecule here that has 4 carbons, and we generate citrate, which has 6 carbons. Okay, so we generate citrate, which has 6 carbons. Now look at this water coming out. This is interesting. So this water is pulled out of here, and we're going to use water. We're going to take water out and put it back in a whole bunch of different times. So water's pulled out here, but then it's put right back in. So basically no net gain or loss of water. It's just pulled out and put back in. And then what happens is we create this high energy electron molecule, an NADH, as we change this molecule around. And then we keep changing it, and we keep changing it, and eventually we pull out a carbon dioxide. So there's one of the 2 carbons that we just put in. There's one of them. And then we change the molecule again. We make some more energy. Here's a second NADH. And we pull out another carbon dioxide. Here's another carbon dioxide. So essentially that acetyl-CoA that we put in that had 2 carbons up here, this acetyl-CoA, we've now removed all those carbons. We've pulled them out. We've taken all the carbons out of that we put in out now. And we pull them out in the form of carbon dioxide. So acetyl-CoA goes in and carbon dioxide comes out. When we do this, we generate these NADH molecules, we generate, in this one it calls it GTP, but essentially it's the same thing as ATP, and we're just going to call it ATP to make our life simple. ATP, essentially it's not, but it works the same. And then over here we also generate an FADH that's just like that NADH. And we generate another NADH up here. And then eventually we end up with malate, and then we go right back to where we started. So the whole process in a couple sentences. We add acetyl-CoA. We run it through this process that generates 3 NADH and 1 FADH, and it also generates an ATP. For every acetyl-CoA, for each acetyl-CoA we put in, we get 3 NADH, 1 FADH, and 1 ATP. So that's what this cycle does. Now, remember when we took glucose, and we broke it down into 2-pyruvate, right? Pyruvate. Then we took those 2 pyruvates and broke them down into 2 acetyls. Well, that means that for each molecule of glucose, we get to run this process twice. We get to run it twice. So we generate double the amount of energy for each molecule of glucose because we can run the citric acid cycle or the Krebs cycle twice. So that's a Krebs cycle. Very, very important process. Takes place in the matrix of that mitochondria and that fluid. Very important.